Today what we're going to look at and start looking at are these models. This is the last unit we're doing. We'll finish this today and tomorrow. Monday we'll spend some time wrapping up and taking questions about this and then reviewing some, and then Wednesday will be your test. But there are 5 main models, the first 2 of which we've actually already dealt with to a degree. And whether you've realized it or not, you've done a little bit with a couple of these others just in solving the equations that you've been solving. Okay, and you've solved some problems related to these. The exponential growth and decay, we have a times e to the bx, or b will be negative if it's a decay problem. One thing to relate this to is one case where we have already used this exponential growth, and that is in the sense of interest. Remember, our amount at any given time is the principal times e to the RT power. Okay, these are the same formula. It's just this one is specialized for the situation of compounding continuously with our interest. Okay, but you can think of this the same way. The P was our starting amount, right? So A in our exponential growth model is going to be kind of your starting amount, or the amount when x is 0. Okay? Notice the thing that the t was multiplied by was our rate, our growth rate, or decay rate if it's a negative. Well, look, the b is multiplied by the x. That's going to be your rate of growth. Now, the difference here is we might be talking about bacteria growing over a certain number of hours. That b is going to be our growth rate per hour. Or we might be seeing, we'll see an example of fruit flies and their population, how it grows over a number of days. Well, the percent that you get up there for B is going to be our growth rate per day. All right, so we'll see that a little bit more as we move forward. Okay?
Question? Are you going to have to memorize these tests?
Well,
if I use the logistic growth model, we'd have to.
I'll explain.
Okay.
So, okay. These 3 models down here, you are not going to have to write yourself. But I do want you to be able to do a couple things with them, and this we'll get into more tomorrow. I want you to know their names. I want you to be able to recognize, if I gave you an equation in this form, recognize which model it is. Now notice, they're pretty significantly different. Okay? This kind of looks like exponential growth, but you've got this negative and the x is squared. Alright, so that's kind of indicative of the Gaussian model. Here it's 1 over, and you've got, this is just like the one we were just looking at with the volume in the forest or whatever. Okay, you have 1 plus be to the negative rx. You've got this logistic growth model. And then also a logarithmic model. You guys have already worked with logarithms, okay? So you should already know what those look like. So really the only 2 new ones are this Gaussian and logistic growth ones, okay? The reality is you've actually already worked with Gaussian models, you just haven't used the equation for it before, okay? Another name for a Gaussian model is a normal curve, okay? A bell curve. This equation right here will give us a bell curve. Okay, so when you see a graph that looks like that, you're dealing with a Gaussian model. Okay, and as you guys already know, normal curves are used to model all kinds of stuff. Alright, so the logistic growth model is really kind of a cool model because this takes into account how something can start growing exponentially, but then there might be something that will impact its growth and cause it to level out. It actually looks like this. Okay? This was actually the one that had the volume of the lumber in the forest. Remember we said that this is what it would look like. It has a bottom horizontal asymptote, and it has a top. Okay? This can be used for a couple of different things. One might be, let's say you're the security chief for the like Sun Life Stadium, okay? And you've got to make sure that security is ready to handle when people get there, okay? For a game. Well, check this out. You're going to have people who get there super early for the game, but not very many, right? You've got a few. Then, as you get to like the hour, maybe hour and a half right before game time, that's right there. You're going to see your population grow inside the stadium really fast. Okay? So, you see this real rapid increase. But, obviously, the stadium only holds so many people. We only sold so many tickets. So that's where this top horizontal asymptote comes in. And you've got these people who show up halfway through the first quarter of the game or whatever.
They're real fans.
For some reason. Yeah, they're not real fans. I don't know why you'd pay $60 for a ticket or more and show up halfway through the first quarter. But anyways, you have these guys. So we still need some security at the gates and whatnot, but not as much as, say, right here. Okay? So that's how we could use that model. This is also a kind of model that they could have used back last year when there was that Ebola outbreak. Okay? You have a couple of people getting sick. And the number of people getting sick is growing a little bit. But then, by the time we realized that we had an epidemic, it was already in this very steep growth time period. Okay? But what happened? They started quarantining people, they started treating people. That lowered the amount, and it was able to level off. And eventually, you can get that you have another logistic decay model to see how it
Isn't it kind of like the Gaussian?
What?
It's like normal, like something like that.
Well, it's not Gaussian completely. It's just you would have another model for going down, but anyways, that's the kind of thing that the logistic can be used for. And like I said, we'll talk about that one more tomorrow. Okay. Today, though, what I want you guys to be able to do is tie something we did at the beginning of the year to what we're doing now, so that you can come up with these exponential growth and decay models on your own. Okay? Just as an example of how these models can be used. You've done some examples of these already, but for example, here's a case where we have a model of the population of the whole world. Okay? We started the time, if t equals 8 represents 1998, then when did we start the time?
90.
1990. Okay? So for this model, t equals 0 would be our population in 1990. What was the population in 1990? 5,400 millions of people. So that's 5.4 billion people. Okay? As you can see here, we hit 6 billion people somewhere in 1999. Okay? And then we could, once we have this model, we could then say, okay, well, hey, what's the population in 2015? Well, you just plug in 25 for t, because it's 25 years since 1990, and you could figure it out. Okay? You could also use this, like they ask here, when does it hit 6.8 billion people? Well, when is it? It's past 2007, but according to our model, we could set this whole thing equal to 6,800 to represent 6.8 billion people, and then we could solve that equation, okay? So that's the kind of stuff you actually have done a little bit of already in some of the word problems that we've worked with.
Mr. Hickson?
Yeah.
Wait, I'm kind of confused what you want us to do. Do you want us to like make up real world examples of these, or do you want us to like relate it to like something we've already learned in the class?
No, that's what we're getting to. You'll be given a case where you recognize that there's exponential growth.
Okay.
You're going to have to come up with this kind of a model, okay?
I think it's 16 billion.
16 billion according to the model?
Yeah.
Okay, that actually shows us the danger of extrapolating models too far. Okay?
Like for 2015,
Our data only goes up to 2007.
I got 7.26 billion.
You got
For
7.26
Yeah,
for 25?
2015, yeah.
What did you plug in?
25.
You plugged in 25?
Wait, let me.
Okay. It doesn't matter, okay? But we are running out of time, so I want to make sure we cover it.
Oh.
Another thing here is you could do it with carbon dating, decay, to estimate the age of a particular fossil that you find. All right, that's another case where we could just plug in this for R and solve, and we could estimate the time. Okay?
Will R always equal 1/10?
No, that's just an example.
Oh, just an example.
Okay. What I really want you guys to do, because this is all stuff that you know how to do already, it's just plugging it in and solving an equation. What we haven't done yet, though, is this. Okay? Here we have a research experiment, and the population of fruit flies is increasing according to the law of exponential growth. Okay? After 2 days, there are 100 flies, and after 4 days, there are 300 flies. So we want to know, how many flies are there going to be after 5 days? Okay? Fruit flies reproduce really, really fast. That's why they're used a lot in genetic experiments, especially in school. If you haven't done one already, you'll probably do an experiment with fruit flies at some point. Okay? But here we have this model, y equals ae to the bt power. It's exponential growth. We got to figure out what a is and what b is. Okay? A is our starting amount, remember?
So 0.
No. Well, you can't start with 0 flies and end up with 100, right?
Yeah, I guess.
So we don't know how many we started with. Okay? We also don't know what the rate of growth is. But what we've been given here in the information of the problem is 2 points in the situation. We've been given a point where t is the number of days and y is the number of flies. Okay? So one of the points that we have is the point to 100. And the other point that we have is the point for 300.
We can set that up in like a ratio, like 2 days are 100, and 4 days are 300, and cross multiply.
We will use a ratio, but we got to be careful how we set it up. Check this out. We've got to use our model. Okay? We're going to set up a system of equations, and we're going to use the ratio to help us solve it. Okay? So if I start with 300 equals a times e to the 4b power. Notice I just plugged in the 300 for y and the 4 for t. Is everyone with me on that? Okay. Then I have 100 equal to a times e to the 2t power. 2b, yeah, thank you. 2b power. And then, like Carly said, we're going to use a ratio, alright? What's the, how am I going to solve this system using ratios?
Maybe like 300 over
Elimination.
100 equals a times e to the 4b over a times e to the 2b.
Yes. And Guys, does this ring a bell?
Ratios.
What else did we solve exactly this way? What else did we find exactly
The
this
last
way?
question?
In the first unit we covered this year. What was our,
It wasn't the patterns,
not probabilities, the
It
unit
was,
before that.
sequences.
Sequences and series. What kind of series?
The geometric series.
Yes, you remember
Oh.
finding the definition A sub
Oh,
n?
you gotta be kidding me.
You had to figure out what R was.
Oh!
Yeah.
So you had to set up the proportions so that
Yeah.
the a sub naughts canceled out, or the a sub ones canceled out, sorry. So we have 3 equals, now instead of having r to a power, we have e to a power.
Wait, why do we cancel out A?
And then we gotta take the.
Because it's a fraction, and it's
Exactly.
multiplication.
So if they're the same, but aren't we crossing out the ones which are different sizes?
Dude, they take the
Like plus
natural.
or minus?
Well, in this situation, the a, oh, you're thinking linear. Like a
Okay.
positive 2x minus 2x and they cancel out to 0. Here we're using a proportion, so the fraction, and we can reduce those a's down to 1. Okay? Now though, instead of having like r to the 4th power and we had to take the 4th root, now we have e to the 2b power,
Natural one.
and we've got to take a natural log of both sides. So ln of 3,
It ends up coming out to be like 0.55.
yes. So the ln of 3 equals 2b, and that means b equals, it comes out to a 0.55.
5.
Alright? That means,
You didn't really start with the whole fruit fly?
No, no, no.
Right,
that's our rate of growth. Our population of fruit flies is growing almost 55% per day. That's why they use them in those genetic
Wait,
experiments,
so that's
because they,
population growth?
yeah, that's our population growth. So now we can come back here, use our 100 equals a times e to the 2 times b power, and figure out what a is, okay? Now, if you didn't round at all,
We did 5 by A and we what did we do?
hang on, well, you just solve for a. This is just a number, right? If you don't round at all, you keep your whole answer in here, this actually equals 3,
Oh, it does.
okay?
Yeah.
Yeah, it does. So,
Convenient.
yeah, it was set up nicely for us. So A is 33 1/3. So we started with 33 fruit flies and evidently 1 egg that was just laid. Okay? So we had 33 1/3 fruit flies to start with. So our model is this, just to put it all together. Y equals 33 1/3 times e to the 0.55 t power. Okay?
That's not bad.
So, I want you to be able to come up with those models on your own.
Oh, that's gonna be